Net change and applications. The integral of a rate of change is the net change. So as we look here, we are integrating from a to b, and we have a derivative here that we are integrating. And so what we end up getting is f of b minus f of a, which is the net change. There's lots of applications in the sciences of this, so let's see some applications and then we can see exactly what this means. If V of t is the volume of water in a reservoir at time t, its derivative, V prime of t, is the rate at which the water flows into the reservoir at time t. And if we integrate from t1 to t2 of this derivative, we would get the volume at t2 minus the volume at t1, which would be the net change of water in the reservoir. If C of t is the concentration of the product of a chemical reaction at time t, then the rate of reaction is the derivative of this. And if we looked at the integral from t1 to t2 of this derivative, we would have this net change in the concentration of the product of the chemical reaction. If the mass of a rod measured from the left end to a point x is m of x, then the linear density is rho of x, and that is the derivative m of x. So if we integrate from a to b of this rho of x, we have the change in mass mb minus ma. If an object moves along a straight line with a position velocity s of t, then its velocity v of t is s prime of t. And then if we integrate from t1 to t2 of this velocity, what we get is the net change in position. So we have s of t2 minus s of t1. So if we integrate t1 to t2 v of t dt, we have the net change in position, s of t2 minus s of t1. If we integrate the derivative of something here, we end up with the net change. Now this is net change, so this would tell us at t1 this object was at a certain position, at t2 it was at another position, and it would tell us how far apart those positions were. It wouldn't tell us if the object had gone back and forth. It would just tell us from where it started, the distance or difference between where it stopped. If we want to calculate the distance during the travel, what would we do? Is we have this velocity curve. If the velocity was ever negative, then this value is going to go below the x-axis, and essentially if we computed the integral, we would get negative for this a2, and we would have a positive, and we would have a positive here. And that is why if we did the integral from t1 to t2, we would have the displacement. We would have from t1 how far it was now at t2. Some of this negative would cancel some of this positive, so we would not know its distance. We would just know its displacement. So if we wanted distance, we are going to have to do the absolute value, or we are going to have to take any areas that are below the curve and then make those positive to sum those up. So if we just computed the integral, we would have net areas, which in the case of getting a position, we would have displacement. If we want distance traveled, we would need to do the absolute values, and then anything that was below, we would take the absolute value and we would have a positive representing that area, and they would all sum together, and that would give us the distance. So just sort of a summary again, if we are integrating and it's a velocity, you need to be careful, because if you go below the x-axis here, looking at the graph, which would mean that the velocity was negative, you would essentially be going the other direction, and so when you compute the integral, you will just have the distance from where it started to where it stopped, not if it went back and forth, the sum of the total distance. You would just have the displacement. And if you needed the distance, you would need to do the absolute value so that these would sum together. The acceleration is the derivative of velocity. So if we had something and we were looking to see how its velocity was changing, if we integrated from t1 to t2, we would have the net change in velocity. Let's look at an example then to see how to apply this. A cyclist pedals along a straight road with velocity in miles per hour given by this quadratic function, and it's valid for t between 0 and 3 hours. Graph the velocity function over the interval 0 to 3, and then we're going to determine when the cyclist moves in the positive direction and when she moves in the negative direction. That's why this graph is going to be helpful. So I am first of all going to factor out a 2, and then once I get this 2 factored out, I'm going to see if I can factor this quadratic. Looks like I've got t minus 3, t minus 1. So we have x-intercepts at 3 and 1. So if we were graphing this, it says to do this between 0 and 3. At 0, we can easily put 0 in this function and see we are at 6. And then we know the intercepts are 1 and 3. So this graph would be a parabola that does something like this. And we are interested in the values between 0 and 3. So when does the cyclist move in the positive direction? Well, we just need to see when the velocity is positive, and we see that is between 0 and 1. So positive direction would be from 0 to 1 hour. During that time, she would be moving in the positive direction. Then we want to know when she moves in the negative direction, and so that would be between 1 and 3 because our velocity value is negative. So we would say from hours 1 to 3, she would be moving in this negative direction. Find the displacement of the cyclist on the time interval 0, 1, 1, 3, and 0, 3 and interpret those. So first of all, we're going to integrate from 0 to 1. That will give us the displacement then. We've got 2t squared minus 8t plus 6 dt. And doing an antiderivative, it looks like we got 2/3 t cubed minus 4t squared plus 6t. And we want to evaluate that from 0 to 1. So putting a 1 in there, it looks like we have 2/3 minus 4 plus 6, and then if you subtract the lower limit, of course that would be 0 for all of these because they all have t in them. So combining those, I get 2 and 2/3 or 8/3, and what that would be miles. So what that tells me is in the first hour she moves to the right by 8/3 or 2 2/3 miles. Now let's go ahead and look from 1 to 3. So essentially this would just change this 1 and this 3. So if we evaluate this at 3, 3 cubed, but one of those will cancel, so that's 9 times 2, that's 18, minus 3 times 3 is 9, times minus 4, so that's 36. Putting a 3 here, that's plus 18, and then subtracting the f of 1, and I've already computed that above, so that would be 8/3. Looks like these cancel out, so I get negative 8/3. Now, what does that mean? Because the velocity is negative, it means that the cyclist is going now to the left. Let's say the cyclist went to the right, because we're looking along a straight road here, and now the cyclist is going the other direction and traveling the other direction 8/3 or 2 2/3 miles to the left. Now if we integrated from 0 to 3, we know that integrals add, and so if we had the integral from 0 to 1 of this function plus the integral from 1 to 3 of this function, that would equal the integral from 0 to 3. Because we have a continuous function, we can go ahead and sum the two. If we sum the two, we get 0 because we had 8/3 and negative 8/3, and so the integral from 0 to 3, or the displacement from 0 to 3, is 0. Well, what does that mean? Well, that means in the first hour the cyclist went 8/3 of a mile in the positive, we're going to say to the right direction, and then from hours 1 to 3 the cyclist went 8/3 of a mile to the left in the negative direction, essentially back where she started. So we get 0 for the integral because the displacement is 0, because if you looked and said where is she at time t1, okay, where is she at time t2? Oh, same place. Because if we looked at this, if this is where she started, she went over here, and in 1 hour she was over here 8/3 of a mile away, and then in hours 1 and 2 she started coming back, and by the time hour 3 hit she had traveled negative 8/3, so she would be back here at 0. So if we wanted to know the distance traveled, we need to sum those two together, because she went 8/3 to the right and then another 8/3 to the left, or 16/3. So this would be 5 1/3 miles. Let's go ahead and just look at this graphically. So here is our velocity graph, and we found between 0 and 1 that this area was 8/3. And then we found from 1 to 3 the integral was negative 8/3. Therefore, if we did that absolute value, this area would also be 8/3. But that would tell us that the displacement was 0, went 8/3, and then back by 8/3. However, if we needed distance, we would take the absolute value, and so we would sum the two together and get our 16 thirds.